To avoid being scammed when buying a plane, especially a second-hand one, you need to know that planes have a lifespan, and it involves 3 calculations. First, there's the number of flight hours. The lifespan of commercial planes in terms of flight hours is generally 60,000 to 80,000 hours. Over 80,000 hours, they're considered old. Don't buy it. Second, there's the number of takeoff and landing cycles, also known as flight cycles. Commercial planes usually have a takeoff and landing cycle lifespan of 40,000 to 60,000 cycles. Over 60,000 and they're old warriors. Third, there's the natural lifespan, which is the accumulated time since the plane started service. The natural lifespan of commercial planes is about 30 years. There are planes over 30 years old, but it's usually out of necessity. For example, Iran retired a Boeing 707 in 2013, which was over 35 years old. Do you think they didn't want a new one? They couldn't get one. These 3 lifespans are an or relationship. When anyone is reached, the plane needs to be retired. Wide-body jets flying long-haul transoceanic routes have longer single flight times, so they might reach their flight hour limit first. And what about planes flying short-haul regional routes? They're like workhorses, flying several trips a day. Usually they reach the cycle limit first, but if an airline is laid back, they might stretch it to the natural lifespan. But that might end up being unprofitable. No one buys a plane just to park it on the ground for show. Note that these 3 lifespans apply to pressurized commercial planes. If your budget is limited and you buy a general aviation plane or helicopter, you don't need to worry about lifespan because these fly at lower altitudes. They usually don't need to be pressurized. So the fuselage doesn't undergo pressure differential cycles from takeoff and landing. Just do regular maintenance and replace any parts that break. If something breaks, just swap it out. For example, the famous air tractor AN2 known as the Y5 in China. Many of the ones flying are old planes that might even be older than you, and they are considered workhorses. But large commercial planes fly high and must be pressurized, so each takeoff causes the fuselage to expand, a process known as stress cycling. Material subjected to long-term or repeated loads develop small damages that gradually expand. In the end, it'll just snap with a crack. This is professionally referred to as material fatigue, or fatigue in English. Whether it's wood, rubber, plastic, or aluminum alloy, or stainless steel, none can escape fatigue. Even if the stress of each cycle is far below the material's yield strength or ultimate stress, doing it once or twice is fine, but over time, it'll break. Reading this, you might just burst into tears after coming home from overtime work. Even steel gets fatigued, let alone people. Due to material fatigue, even regularly replacing parts or engines won't solve fuselage fatigue issue. Unless you replace the fuselage, which raises a philosophical question. Is a plane with a replaced fuselage still the same plane? Fatigue is a long-standing problem in mechanical design, whether in aviation, automobiles, or bridges. For instance, Delta Airlines in the United States lost the flaps of a Boeing 737 for 2 consecutive months in July and August. It's the first time I've seen a subscription-based flight accident. The reason for the flaps flying off is most likely due to metal fatigue. Since the Industrial Revolution, engineers have been puzzled by train axles that break after a period of use. At the same time, they began a difficult search for answers. How long can this structure last before breaking? It wasn't until the mid-19th century that German engineer August Wöhler discovered that the lower the stress amplitude, the more cycles a material can withstand. He conducted numerous experiments and plotted the famous SN curve with stress amplitude as the vertical axis and cycle count as the horizontal axis. Over 100 years later, the SN curve remains the most basic and widely used method for fatigue analysis, especially for high cycle fatigue, which involves low stress cycles exceeding 10,000, and it has proven to be consistently reliable. Many industries have their own material manual. For example, China's aviation industry has an aviation material manual spanning 10 volumes and 11 million words. It's the wisdom crystallized from predecessors' battles with fatigue. Looking at the SN curve, have you noticed it declines more and more slowly? Especially steel, it seemed like there was an asymptote. This means that if your stress amplitude is very small, the number of cycles is nearly infinite. In other words, as long as the force on the material is small enough, you can assume it will never fatigue. But unfortunately, not all materials have SN curves like this, such as the aluminum commonly used in airplanes. There's virtually no asymptote, meaning that even if you apply the smallest force to aluminum, as long as the cycles are enough, it will eventually fatigue and crack. Anyway, with the material's SN curve, you can find the fatigue life based on stress. But how do you get the stress? Finite element analysis? Many finite element software now integrates fatigue analysis tools, such as Tianfu's structural analysis software AIFEM. It can calculate stress and fatigue. The 2025 R1 version includes an introductory case for fatigue analysis, guiding you step by step on calculating the fatigue life of perforated plates under cyclic tensile forces. I ran through the case, and from the results, you can see the shortest lifespan area is indeed at the hole, which shows that stress concentration accelerates metal fatigue. How terrifying is the combination of stress concentration and metal fatigue? The British experienced this over half a century ago when the square windows exacerbated stress concentration, leading to 3 crashes of the Comet jet. It was also a valuable lesson for engineers around the world. I hope that after watching this video, whether you're designing planes or buying them, you won't fall into the trap of material fatigue using structural simulation software AIFEM to produce parts that meet strength and life standards.